Hi friends, welcome you all to Magical Physics. So in this video session, we're just going to talk about an important concept called electrostatics, where we are just going to look into an important concept which is the application of Gauss law. So when we just come about a Gauss law, we just come with the idea where we just study the electric flux which is being given with the concept of the charge enclosed by the Gaussian surface. And when you just talk about the application of Gauss law, the content what we are just going to look into right now is about electric field due to an uniformly charged spherical shell. So I have just taken a uniformly charged spherical shell where I'm just going to look into the electric field what has been produced due to the charged spherical shell. So first of all, I consider a uniformly charged spherical shell with a radius of r and the total charge q. And I'm just going to find out the electric field at points outside and inside of the sphere and also on the surface of the sphere using Gauss law. So first I consider the case where I have taken a point outside the shell. So the point P is taken outside of the shell at a distance of r from the center of the spherical shell. And if you just notice, the charge is uniformly distributed all over the surface of the spherical shell, which resembles a spherical symmetry as shown in the diagram. So here just look at the diagram A, where we have just considered a sphere of radius r, and we have just taken a point P which is outside of the sphere with a distance of r. So if you just notice, the distance r is greater than the radius of the spherical shell. And as we just consider a uniformly charged spherical shell where the charges get distributed uniformly all over the surface of the spherical shell and which resembles a spherical symmetry. So due to it, we consider a Gaussian surface which is spherical in shape. We consider a Gaussian surface which is spherical in shape, which is given in the diagram as shown. And if the charge Q is greater than 0, which means that the charge is positive, then it means that the electric field points radially outward from the spherical shell or the charge. And if Q is less than 0, which means that the charge is negatively, which denotes that the electric field points inward. So as we have just chosen a spherical Gaussian surface of radius r, the total charge enclosed by the Gaussian surface is going to be Q. The total charge enclosed by the Gaussian surface is going to be Q, what we have just taken. So we have just chosen a spherical Gaussian surface because the charge is uniformly distributed, which resembles a spherical symmetry. So the next what we are just going to do, we are just going to apply the Gauss law. So on applying the Gauss law, we just know the formula of total electric flux, which can be just given with pi of E is equal to closed interval of E vector dot dA vector, which is equal to Q by epsilon naught. So this is the equation what we just know for Gauss law. So here what we are just going to do is, if you just notice the direction of the electric field which points radially outward from the spherical shell and the direction of the area vector, they both are in the same direction at all the points on the Gaussian surface. So just consider, this is the surface what I have just taken and which has been completely filled with the charges. I mean the sphere what I just consider, and I have just taken a Gaussian surface around it. So if you just notice, the electric field points radially outward if the charge is going to be positive. If the charge is going to be positive, where the electric field points radially outward. And I just consider a small area on the surface of the on the surface. So here if you just notice, the direction of electric field as well as the direction of normal vector of area, both are going to be in same direction. So if both are in the same direction, which means that the magnitude of electric field is going to be same at all the points due to spherical symmetric of charge distribution. So now what we just do, we just make a modification on this equation as the electric field and area points in the same direction. This equation can be just written as integral of closed integral of E dot dA is equal to Q by epsilon naught. This is the equation what can I just written. So the vector form has been removed as which we just represent with E dot dA cos theta. So if you just notice over there, where electric field and the area points in the same direction, where theta is going to be 0 degree. If theta is going to be 0 degree, where we just get the value cos 0 is equal to 1. So the equation gets modified like this, where we just remove the vector form. And next thing, the magnitude of electric field is going to be same at all the points due to spherically symmetric of a charge distribution. So what we just do, we just take out the electric field out of integration, and right now we are just going to integrate only the area. So on integrating only the area, the total area of Gaussian surface, which will be just given with 4 pi r square as it is spherical. So now we just substitute the value in the previous equation, where we just get E dot 4 pi r square is equal to Q by epsilon naught. So what we are just looking to in this concept is about the electric field at a particular point P outside the shell. So we just want to find out the electric field. So we just modify the equation and we just get a final equation, which is E is equal to 1 by 4 pi epsilon naught Q by r square. So which is given in the form of magnitude. This is what given in the form of magnitude. So I just need in form of vector. So if you just want in form of vectors, we can just represent E vector is equal to 1 by 4 pi epsilon naught into Q by r square into r cap. The above equation gives an idea that electric field at a point outside the shell will be same if the entire charge is going to be concentrated at the center of the spherical shell, where if the charges whatever I just consider, if they just get concentrated at the center of the spherical shell, which means that the electric field at a point outside the shell will be same. This is what the final conclusion what we just come from. So the next condition is about a point which we just consider on the surface of the spherical shell. We just consider on the surface of the spherical shell. So when you just talk about on the surface of the spherical shell, just look at here. I have just taken a spherical shell and I just consider a point P, which is at a distance of r from the center, if you just notice. And we also know the radius of the sphere is capital R. So where now the condition relates us distance is equal to the radius. This is the condition what we just get related. So we have just found out the electric field at a point already using Gauss law. So we just come with the same idea of this equation, which is E vector is equal to Q by 4 pi epsilon naught R square into R cap, where in the previous session we just discussed with the distance, square of distance, and here we just substituted, instead of small r we just substitute capital R, which is nothing but instead of distance we just substitute the radius of the spherical shell. So the next condition is about at a point inside the spherical shell. So we have just seen about the two conditions where we just consider a point P either outside of the cell or on the cell, where what is the amount of electric field experienced over there. So right now what we just do, we consider a point which is present inside the spherical shell. Just consider this, if this is going to be your spherical shell with a radius of R, and I just consider a point P which is present inside the spherical shell, and just consider this will be in a radius of a distance of R. So this is the Gaussian surface what I just consider. This is the Gaussian surface what I just consider right now. We always know the formula about on using the Gauss law. We just get an equation of that E dot 4 pi R square is equal to Q by epsilon naught. It's okay, but we know the properties of Gauss law or the Gaussian surface. So whenever you just talk about Gaussian surface, it encloses charges, but here the charge get distributed, as we have just seen initially, the charges get distributed on the surface of the shell. Uniformly charge get distributed on the surface of the shell. So if you just look into now, where the Gaussian surface do not encloses any charge, where the Gaussian surface do not encloses any charge, as the charges are on the surface of the spherical shell, the Gaussian surface what we have just considered is present inside the shell, so which do not encloses any charges. So due to that, Q is equal to 0, so the entire equation becomes 0. So if you just look into the electric field what has been experienced by a point present inside the spherical shell will be equal to 0. So these are the conditions what we have just seen on the application of Gauss law, where we just discussed about the electric field due to a point uniformly charged spherical shell. So I hope that you all have just understood the concept very well. So if you have just not subscribed to our channel, please subscribe our channel Magical Physics, and please do refer to your friends about our channel. If you just like this video, please give a like, comment, as well as share along with your friends. Thank you. Have a great day.